Okay, so let me begin by thanking the organizer for giving me the opportunity to talk here. This is an work which is kind of ongoing. Part of it has been put up in the archive some time back, and the other one is with other one is with Shaurin, who is here. My PhD student Sanam Khan, Utkarsh, who is also here, and one of the PhD students of Utkarsh. Okay, so here what I am going to talk about is basically quantum teleportation in the fermionic setup, and in the end I will try to talk about also how to implement that with using these Majorana zero modes. Okay. So quantum teleportation, it's at the heart of quantum communication. So if you want to send information encoded in terms of quantum states, then and without physically transmitting the quantum system, then this is one of the best ways to use this quantum teleportation. Now, if for quantum teleportation, what you need is a shared entangled state between the sender and receiver, and as you know, entanglement is very fragile because the quantum systems are prone to interactions with environment. So the question is that if sender and receiver they share a maximally entangled state, then you are done. You can do this quantum information exactly, quantum teleportation exactly. But if it is not maximal entanglement, then what do you do? So back in 1999, these Horodeki families, they are quite famous in quantum information parlance. So they have shown that if you have a state, a bipartite state, which is between the sender and receiver, and if that state has some amount of entanglement, then what is the best teleportation fidelity that one can achieve? And that best teleportation fidelity is given by this quantity for d-dimensional system. If you want to send the states of d-dimensional system, so f max times d plus 1 by d plus 1, where this capital F max is what is known as the maximum singlet fraction. So if you have your shared state, what is the maximum overlap of it with a maximally entangled state? But this is for standard quantum theory, where we can only consider system of distinguishable particles. So what happens if we want to go beyond system of distinguishable particles? Say for example, if I want to do quantum teleportation with fermions, okay, so what will happen to that? And this fermionic quantum information theory is not very old, and people are now using it for information transmission, for metrology purpose, dense coding, etc., etc. So this is it's an interesting question to look at, right? So the question is that so for fermionic system, there are two kinds of entanglement. One is called the particle entanglement, where you look at, so the number of particles shared between the two parties is fixed, but there you get to see the entanglement between the particles shared between one party and the particles shared between other parties. And there is also the mode entanglement. So the mode entanglement is something where you don't restrict the number of particles. So here the entanglement is between the modes shared between two parties. So what we will talk about here is basically using mode entanglement, and this for mode entanglement. So what we will do is in a generic case where n cross n mode. So there are two parties, sender and receiver, Alice and Bob. So Alice has n mode system and Bob has n mode system also. They are fermionic system, and we would like to see what is the best way to teleport quantum information encoded in terms of n mode fermionic system states. Okay, so I will not go into the details. So when you deal with fermionic system or system of indistinguishable particles, one should be little bit careful, because the thing which we do with standard quantum theory, quantum information theory for system of distinguishable particles, more or less they will hold good, but you should be little bit careful in the sense that whatever quantity you define, either it is teleportation fidelity or some other quantity, you should do it in operational form, okay, not in just mathematical form. So for example, if I want to figure out that the teleportation, how to figure out that my teleportation process for fermionic system is working well. So in standard quantum theory, what we do, we take input state at the sender's lab and then send it through the shared state, and in the output at Bob's lab, I look at the output and look at the overlap of the output and the input. And if the overlap is close to 1, we say that this is a good teleportation. In this case, in the case of fermions or indistinguishable particles, we should not do that, because what we need to do is, let's say I have, so in the case of fermions, what we need to do is we cannot send state of a single system, okay. So what we need to do is what is known as entanglement swapping. So I have a bipartite system, and state of one part of the system I would like to teleport, so that after the end of the teleportation, this entanglement will be shared between the two labs, okay. So then what we need to do is we take this state where the part of this A tilde has to be teleported, and this is the shared state between the sender and the receiver, and the quality of the teleportation can be judged by performing operation. This is a kind of measurement on this A tilde part, or this is some kind of operation, not necessarily measurement, it can be unitary also, but this is a measurement. This measurement is acting on this A tilde and A part together, and then based upon the measurement outcome, which is x, on the Bob's lab, Bob will do some operation, okay. So, and what we need to do is to check whether these two quantities are same, and that will give you basically the teleportation fidelity. Okay, so this is the schematic. So this is sender and receiver, they share some fermionic entangled state, and then in the sender's lab there is this entangled state, this part A tilde part has to be teleported to Bob's lab, and there will be some classical communication as in the case of standard teleportation. Okay, so what we will talk about is we will talk about these in the simplest case where we have 1 cross 1 mode system, and for teleportation, and then I will briefly talk about how to realize it with Majorana zero mode. Okay, so this is the outline of my talk. So let me go to this first part. So here what we do is, so for fermionic system, in this particular case we will consider these PSSR, that means these parity superselection rule, okay. So in other words, it tells you that if I take my fermionic system, if I take a state, let's say pure state, it can be mixed state also, I cannot take linear superposition of even parity states and odd parity states. So I can only allow only even parity states, superposition of even parity states, or superposition of odd parity states. So there are some principles of nature for which you will have to do that. I am not going into that. So basically what we will consider at state level, we will consider these PSSR restricted states. Operational level also will take PSSR restricted states. Okay, so let's say, so there is something which is important when we talk about teleportation. So there are two kinds of entanglement. These are just examples. So for example, if I take a state like this, so this is even parity state in Alice's system. So now I am talking about 1 cross 1 mode, and this is even parity state in Bob's system. Similarly, this is the so this even parity state maybe you can consider as the vacuum, and E2A maybe you can consider this application of these two creation operators on the vacuum. So this is again even parity state in Alice's lab. Similarly for Bob. So this is the superposition, and this state is really entangled because you cannot write it as a convex combination of product states. On the other hand, if I look at this state, which is again superposition of, this is even parity state of Alice, even parity state of Bob, and this is odd parity state of Alice, odd parity state of Bob. So this is not in that sense is not an entangled state. Why? Because if I apply the local projectors, okay, which are also PSSR satisfying, then what you will get is basically this superposition, not mixture of these product states. Okay, so that is why we don't call it as basically it is not in that sense an entangled state. Okay, but this state has some correlation which we call as topological correlation, and these kind of states will use for teleportation using these Majorana zero modes. Okay. But once again, these kind of states, these topological correlations are important, for example, for quantum sensings and other things. Right. Okay. So, for example, how to figure out how much topological correlation is there in a state? So, what you look at is you take your state in a bipartite state, fermionic system, and then I forgot to tell you that in a fermionic system, instead of tensor product, you will have to consider this wedge product. Okay, so you consider these trace, and then this should be you should look for this rho tilde f such that this trace will be same as with this rho tilde f. Okay, and you take the collection of all those rho tilde f. Rho f is given, right? And now what you do, you take the von Neumann entropy of this rho tilde f, take maximum of this von Neumann entropy and choose that rho tilde f for which you get this maximum, that we will call as infer of rho f. Okay, and now what you do, you take the difference between this s of this infer rho f minus s of rho f, and that is what is called as this topological correlation. Okay, and you can look at that the earlier example and see that the topological correlation will be basically 1. Okay, good. So, so this is the state what we will consider for our teleportation. This is the shared state, and this is the entangled state, or this is some kind of entangled state whose one part we would like to teleport. Okay, so that is the brief description of the teleportation scheme, and then let me talk about the optimal fidelity, the best fidelity that you can have if you have a noisy entangled state as your shared state. So the scheme to look for this optimal fidelity is the following. I am not going into the details. So basically, you determine a canonical form of the fermionic bipartite state. Rather than looking for all possible teleportation scheme, what you look for is you try to figure out a canonical form of the shared state by doing some local twirling, unitary twirling operation, and take this canonical form of the state and then use it for teleportation. So the canonical form of this shared state is such that it will not change the teleportation fidelity. Okay, so that is the reason, and this is in the same line of Horodeki's work. Okay, so you look for this canonical form, but of course the twirling operation should be local PSSR respected. What you need to do is this unitary 2 design, and then establish this state channel isomorphism, because teleportation is a channel action. So through this Choi-Yamilokowski isomorphism, you can also figure out the channel, right? And then this will determine the canonical fermionic channel under this twirling. Okay, and then you should look for this invariance of this operational entanglement fidelity under channel twirling operation, and then this will give rise to this optimal teleportation fidelity. So let me write down, let me tell you what is this canonical form. So you start with any n cross n mode this fermionic state, entangled state, and then you apply this local twirling operation. What you will get is a state of this form. So this is generally the noisy state. So you take this wedge product of this identity, wedge product of this Sz, which is wedge product of this individual sigma z, and then this is the superposition of this is even parity state, and this is, so this satisfies these local SSSR, PSSR, but this one does not satisfy. Okay, this psi EO, and these are some of these probabilities that one can come up with. Okay. Right. So this part is what is the local parity preserving state, and this part is what is parity violating state. So any n cross n state, fermionic state, can be written in this form by using this this local trilling operation, which is locally PSSR preserving, respecting. Okay. Right. So that gives rise to, because you have this state, you can figure out also the corresponding channel, this E, which is by the Choi-Yamalikowski isomorphism, which works on this maximally entangled state, fermionic state. Okay. So this is the state that we are talking about, and so basically, the state channel isomorphism will give rise to the corresponding state here, and the basis under which you can write. So what is this part? So this is basically up to this first term and second term. Okay, so this is even parity state. This is also even parity state. Okay, and this part is, here it is even odd, and here it is odd even. So this last two parts give rise to this psi n E O. Okay, good. So now under this channel action, I said that the local trilling operation, you can cast any n cross n mode fermionic state into this canonical form, and that will give rise to this channel action through this Choi-Yamalikowski isomorphism, and that gives rise to basically the form of the state like this. Okay, so this is the ultimate form. Okay, this is the noisy part, and this is the exact part. So this exact part, you can use it to teleport exactly, and this noisy part, of course, you cannot do it exactly. Okay, so there are some relations with these parameters, gamma 1, p1, p2, etc. I'll not go into that part. Okay, so ultimately the fidelity that you will get for this noisy channel is this following one. Okay, so if you look at the fidelity of teleportation, it is basically of this form. Okay, and D is the dimension. Okay. Okay, so unlike in the case of standard teleportation with standard quantum theory, here you will have, so in standard quantum theory you will have only this part, which is the singlet fraction, whereas in this case you are dealing with this fermionic system. You have these two parameters, gamma 1 and f, and these are the 2L invariant parameters for teleportation. Okay, so let me skip that. This is basically, this is the the form of this fidelity, and yeah, I'll not go through that. Basically, if you want to take the this topological correlation, then the teleportation fidelity is defined in this way, and with the corresponding Krauss operators for the teleportation channel. Okay, so let me go to the implementation part. Okay, so we are talking about teleportation of 1 cross 1 mode fermionic system state, and so this can in principle be implemented using this Majorana 0 mode. So basically, you have this in mode picture, as I said, the allowed fermionic states and operations, they must satisfy this PSSR condition, parity superselection rule, and practical demonstration of systems satisfying this PSSR can be done with Majorana 0 mode. Of course, the question is, where will you get to see Majorana 0 mode? I mean, that is, of course, the question. We still Microsoft has recently, they claim that they have the Majorana 0 mode, but it's still questionable. Okay. So Kitaev, in this paper, he came up with this Kitaev chain, and this Kitaev chain has this twofold degeneracy with these 0 and 1 fermion states in the ground state basically, and here this, if you look at the two boundary modes, so these are the two Majorana 0 modes localized at the end of the chain. Okay. And such degenerate ground states, it can be used to implement this topological qubit with braiding of quantum gate operation. So the Majorana, I mean, for the Kitaev chain, this is the Hamiltonian that you can talk about. These are the fermionic operators acting on the nth element of the chain. And so basically, this Hamiltonian is exhibits this gap topological phase for magnitude of mu less than t, and it's at a trivial phase for magnitude of mu greater than t. Okay. So what you can think of is, these fermionic operators f, it can be related simply with this F tilde operator, and this F tilde is basically you write it in terms of this Majorana operators, okay, gamma n, gamma 2n and gamma n. Similarly F tilde, so F tilde dagger and F tilde. So like in this case this is kind of theta F chain. So this one and this end one, so gamma 1 and gamma 8, these are the Majorana modes. So this will give rise to these fermionic operators, and this will not contribute anything in the energy, because this Hamiltonian does not depend on the Majoranas present at this at these edges. Gamma, it will not depend upon gamma 1 and gamma 8, and therefore it will not have any contribution in the energy. Okay, so this is the kind of architecture that we are looking into. So this is called hexon topological qubit architecture. So this is one theta F chain, this is another one, this is another one. So you have in the end these are the Majorana 0 modes, and yeah. So this is for a single qubit. So so there is also okay. So let me tell you why this fourth. So basically one fermion you can think of in terms of two Majorana 0 modes, and one qubit you can consider in terms of 2 fermions. So basically 4 Majorana 0 modes will be enough, but this these two, gamma 3 and gamma 4, these are required for measurement purpose. If you do measurement, then you can violate this this parity super selection rule condition. So these will work as ancilla so that it can compensate that violation. Okay, so this hexon architecture has the advantage because it has this Coulomb blockade, and thereby it provides the protection from quasi-particle poisoning. Of course, quasi-particle poisoning protection it can give up to certain level. If it is more than that threshold value, you will have to do error correction there. Okay, and also the measurement for braiding that we will have to consider, that will also incorporate this quasi-particle poisoning. Okay. So ultimately we will have to do error correction here in order to get good quality teleportation fidelity. Okay. And this hexon qubit architecture, it has this advantage of performing this braiding operation using something called measurement only approach. Okay. So basically this measurement only approach, it takes care of this braiding, and this measurement is basically achieved through this tunneling of electron through this Majorana 0 mode, and that these two n Majorana 0 mode will constitute the fermionic mode that we mentioned earlier. Okay, so this is the kind of Hamiltonian that you consider. So basically the for this braiding. So this is a quantum dot Hamiltonian, this is the tunneling Hamiltonian, and this is your system Hamiltonian, which is the BCS and that. And so this NS or NG, this is the charge count on a superconducting island, and this is the control by gate. I'll not go into that details. So basically so this is the quantum dot Hamiltonian. So this is the charging energy related to this island, and this is the tunneling Hamiltonian, and this Ti is basically this T, and this corresponds to tunneling between this quantum dot and Majorana 0 mode. Okay, right. Okay, good. So this and this measurement for the braiding, that can be achieved through different means like the spectroscopy, charge sensing, differential capacitance, etc. And people have done this thing. Okay, right. Okay, I will not go through these details because this is this will take more time. So this is basically, this tells you how this braiding is achieved in the case of this Majorana 0 mode. So let me skip this part. Yeah. So this so therefore this braiding operation, how does it perform using this these fermionic operators? So you look at this. So let me go back to this, maybe I'll just, let me see, let me go back this figure. Yeah, see, this is gamma 1, this is gamma 6, gamma 2, gamma 5, and gamma 3, gamma 4. So these are the Majorana 0 modes. So what you do is, yeah, so you basically you consider this non-local Majorana 0 modes, because the first one, gamma 1, is the first K-type chain, and the gamma 2 is the second one. So this will give rise to this fermionic F1 dagger. Similarly, this is F1, and next you take gamma 5 and gamma 6 on the right hand side, and this is F2 dagger and F2. And as I said, the third chain, Kitaev chain, where you have gamma 3, gamma 4, that will work as ancilla. So you consider these bases. Okay, this is the basis of states in the fermionic system, and you can now take these braiding operators. Okay, so the braiding operator, basically it will look like this for this R12, braiding this gamma 1 and gamma 2. And in that basis, with respect to that basis, you can write down this braiding operator in this matrix form. And similarly, you can look at the braiding between 2 and 5. So gamma 2 and gamma 5, this is the form, and it has this matrix form. So again, you write it using this basis form, okay, using these fermionic basis states. Right. So here is the table. So basically, for teleportation, you need this is 1 qubit, and this is so this is for fermionic single mode teleportation hardware. So this is one hexon qubit, and this is another hexon qubit. Okay, so this is the identification. You have this circuit between, so this is gamma, this is up down you can consider, and that corresponding hexon qubits are these gamma 1, gamma 2, which corresponds to this mode. So for each mode you need these two Majorana 0 modes. Okay, so this is for A tilde prime, A tilde, A B, and this is for the reference one. Right. Okay, so this is the circuit. So you have these gamma 1 U and gamma 1 D, and similarly gamma 2 U, gamma 2 D. So this will give rise to under this braid. So this will consist of the initial state whose part A tilde you would like to teleport. And now this is the 0 0 state with gamma 3, gamma 4, I mean gamma 3, gamma 3 up, gamma 3 down, and gamma 4 up, gamma 4 down. Here you do this braiding to make this entangled state. Okay, so this one is basically entangled state after this braiding, and this is your reference one. Okay, now you do what you do in standard teleportation. You do measurement, then XOR, then X gate, Z gate, and then measurement. So that will give rise to basically the teleportation, and this is the exact teleportation. And so through this exact teleportation, actually you can send a part of the state from Alice's lab to Boss lab. Okay, right. So these are the okay. So these are the braiding operators. And as in the case of standard teleportation, basically you can start with this is the state and this is the shared state. Okay, so this will be your state, and then you apply this braiding operation. Ultimately you can, so this will be the initial state like this, and then if you apply the braiding operation you can get the teleportation. I will not go into this quasi-particle poisoning, because this is work under so what we are still working on this. So we could manage to show error correction due to this quasi-particle poisoning for single qubit, but we need to go beyond that. We need to do at least 2 qubit error correction. So this is what we are currently trying to do. So this is the platform that I said, using Majorana 0 mode. In principle, you can use this teleportation scheme, and because we are dealing with this mode entanglement for fermionic system. Okay, so with this I'll stop. Thank you.
Thank you. Now the session is open for questions. Questions from student side? No? Okay. No more questions. Let's thank again Professor Sivasis Bose for
Thank you.
wonderful talk.